Right, I think it's time to take a look inside this thing now. That's actually a quite heavy piece of metal, not metallised plastic, as I thought. It's quite a chunky piece. Maybe that's just to, wonder if that's just to get the balance. Yeah, I think it maybe just to make it feel a bit more balanced. Something holding it together in the middle. Can't see any other screws though. Just take a quick look before we try cracking it to see if there's any screws hidden in there. Right, yeah, it looks like there is a screw there, so we need to try and figure out how to get to that. Maybe it's underneath the trigger switch. The rest you can see in here, there's obviously, that's the display. You've got the battery connect board, got some wires with sort of ferrite lump on it for noise reduction. Hard to see what we've got here. Getting sort of centre up here and putting a main board in here. You can see a couple of flexes going up to the display. I can see the screw in there. I'm not sure this is quite the way this is intended to come out. It's a sort of shaft on here that the ends. Obviously this shaft needs to pull out of the back of the key rather than just bending across like that, so I need to improvise a little repair on that. Can actually see the screw underneath there. It's not quite clear how you're supposed to get to it. I didn't get enough purchase on this to undo it, but I'm sure there must be a different way of getting that button out to. So I can't see be able to do this up this way, so I'm sure this button snaps in somehow. That seems to have got it. So we've just got this flex up here going to the front keypad. Unplug. And the whole inside comes out as one nice little unit. Okay, I think I've just figured out how this is supposed to come apart. There's a little trim piece in there that comes away, and that's where they've hidden these other two screws. So I suspect if we take this off, this metal piece will come out. Yeah, that comes out, and then this button just lifts out, and there you get the screw without bending it too much. So you'll have to try and put that back together at some point. One little word of warning, when this comes off, this metal piece is only held to the front by these fairly weak clips. Now you don't need to take this apart, but if you do, there's a little spring in here that A can sort of ping out, but B is really tricky to get back in. This is the spring that biases the shutter to be sort of held either open or closed. It basically it goes round here, it's like a coil split, it goes round here, it's got a little coil and then goes sort of back, and the end sits inside the button, and the trick seems to be to actually thread it around here, close it all up, and then just push the end inside the button where it lives. And that works, but be particularly careful sort of just idly flicking this when this thing isn't screwed down, because say these clips pop off, because it's normally held down by the screws. They can pop out quite easily with handling, so just be aware of that and don't lose your little spring. So there's a few more bits of rubber and plastic. There's a rubber bit around the lens, a rubber insert here. Oh, there's a clip holding the camera module in. It's also holding the rubber in. So this looks like a fairly standard sort of video camera module. It's got Truly on there, so I'm guessing this is probably just probably not a ready-made, but certainly a sort of custom or semi-custom assembly based around a standard camera chip, maybe an OV7670 or something similar. That just goes down to a flex onto the main board. There's another bit of rubber on the top here. So all this rubber is going to be to do with the shock protection. So it's got a nice soft mounting inside its case. The LCD is just held on this by this frame. This is actually a metal frame. I'm guessing it's maybe magnesium or something. It's quite light. Everything's obviously held together nice and solidly. So this battery PCB, literally all that's on here is the battery connector and the button. Right, there's another little connector here. I suspect that may be going into whatever it is that moves the calibration vane in front of the thermal lens. I think this yellow clip might be screwed in from the back. So let's pop the LCD off. Looks like a fairly standard LCD module. So on the back of the main board, it looks like we've got pretty much, looks like it's all memory. Got a flash chip there, looks like it's probably some RAM. There's a little battery here for presumably real-time clock. Obviously they're not really intending that to be very user replaceable, because it's quite hard to get to. One interesting little detail, there's cut out in the PCB with a component on here. Now I'm sure what that's, there's actually a metal tab behind it for this frame, so that's going to be a temperature sensor that's measuring the temperature of this frame. Obviously one reason for using a metal frame rather than plastic is to try and keep the whole thing at a constant temperature, to avoid having temperature gradients across it, which are going to cause measurement inaccuracy. So this is getting a measurement of the whole environment of the sensor, but without being influenced by any, because certain parts of this PCB are going to get warm and you don't want that to influence the measurement, so they've actually done a cutout in this PCB to isolate that thermally from the rest of the board, and I'm guessing there might be a little thermal pad or something there coupling that to the little tab in the metalwork underneath. This feels like there's a connector connecting it to a board underneath it. Might help if I unplug this. Right, so here's the main guts of it. We've got that's interesting. We have a button which you can't actually get to from the front. So we have a little secret internal button which says on, off and load. Yeah, there's no way of getting to that at all. Yeah, I can only assume that's perhaps for testing, so they can test the board without having to have the keypad plugged in. But that's interesting. Let's take a close look at that in a minute. So obviously in the back of here we've got the actual thermal imaging sensor. And just confirmation this does run Windows C embedded. There's the license sticker on the side of the frame here. Right, so a close look at this PCB. Here's that little temperature sensor. So that's obviously a silicon temperature sensor that just sits in this little cavity down here to measure the temperature of the whole front and the image sensor. That I'm guessing is an E squared prom just by the pin count and the fact you've got the two resistors for I squared C pull up. I haven't checked the part number on that, it looks a bit obscure. That's the connector to the battery and trigger switch. Keypad connector here. There's an unpopulated connector option there. That's the connector for the image sensor board. A few bits of power management here. Looking at the fact that's next to this, I think that may be what controls the vane, the calibration vane thing, which I'll have a look at if we can find it later. So here's this magic button. The main processor here. This is a Freescale MCI MX257. This is a sort of consumer electronics system on chip thing. There's an ARM 400 meg ARM926 camera interface, LCD interface, so this is handling sort of pretty much all the stuff you'd expect in something like this. Looks like an unpopulated connector footprint there for something. Again, the idea, this board is probably the core of quite a few different products, certainly all the E series, whether it also does the like the E50, 60 and so on high end, I don't know. USB connector, a little chip there, whether that's a USB interface or it could just be protection or something, doesn't seem to be much else around it. And here we've got some power management. This is clearly generating all the various power supplies for the FPGA and the processor. We've got these little inductors there. That's a Dialog DA9021, which has got sort of 3 buck regulators, 5 low dropout regulators, various other bits and pieces, USB charger, so that's doing most of the power management. Crystal there, that's pretty on the FPGA. This is the main FPGA, so Cyclone EP4C40. This is a fairly chunky device. I looked on DigiKey and it's about 45 quid one off, so it's a fairly sort of mid-range FPGA, especially for a sort of a low-end product. But obviously this is also going to be used in the higher frame rate versions, which is going to need a lot more processing power to deal with the higher image resolution. So this is the video camera connector, not the keypad connector. On the back side we've got the LCD connector. That's probably going, yeah, it's going straight to the processor. This flash memory, so this will store all the firmware, but also probably the filing system for the onboard image storage. It's almost certainly going to be a NAND flash. This is almost certainly some RAM, sort of DDR2 or 3, looking at all the wiggly length match traces there. This is a 256 megabit low power DDR mobile DRAM. This is connected to the FPGA, so that's going to be for the local image buffering, maybe also things like sort of per pixel calibration, and a little battery down here. This is a 1388, which is a real-time clock, and there's obviously the 32K crystal next to it. That's providing the real-time clock. A few other little bits and pieces down here, which could be pretty much anything, maybe more power management, and that's about it. So not pretty much what you'd expect on something like this. You know, processor handling all the user interface, running Windows C embedded, and FPGA handling the actual image processing. And clearly, as we saw, when you fire it up, you get an image pretty quickly. So the FPGA is going to be handling the transfer of the image, the thermal image data directly to the display, and probably handling overlaying data from the LCD controller in this thing in hardware. So I'm guessing sort of the LCD interface from this probably goes through here into the LCD. You can actually see the tracking there. Actually, in fact, it looks like the that's the camera connector. It looks like the camera sensor also goes straight to the FPGA. So it may well be doing all the that edge detection stuff for the image enhancement. That's probably being done in hardware as well for speed. And actually, it looks like the LCD connector is going sort of towards the processor, but it's a bit hard to tell. Obviously, this is probably at least a 6 or an 8 layer PCB, so you can't tell a huge amount by what you can see on the surface. But it does look like the LCD is going into the processor. Actually, thinking a little bit more about how this thing is probably working, I'm guessing what they're doing is they're effectively presenting all the data to the main processor as if it was a camera. So they're using the camera interface on this processor to merge in all the thermal data with the visible camera to actually, so that the hardware interface on the main processor, because it looks like the LCD is actually being driven by the main processor. So I think what they're doing is they're taking the signals from the visible and thermal camera, merging all that lot, and then just presenting it to the camera interface on this as if it was just a camera. Because the one thing you notice on the, for example, when you run it off the PC, you always get all the on-screen overlays and everything. I suspect that's what's happening. It's just sort of merging everything in hardware and just presenting an image. Although it's interesting, they still managed to get the display happening before all the Windows stuff's booted up, so maybe they've got some a bit of software that runs right at the beginning of all the boot process that actually just sets up that sort of like camera preview mode type function while the Windows stuff's actually starting to happen. Incidentally, there are a few sort of various test pads here, and you can actually just about see on these ones there's some little dents from the test probes, but these are the only ones that have got any dents on the test probe, so I'm guessing maybe these are a JTAG interface or something that they use to program. Maybe they program the flash, because the flash memory doesn't have any label on it, which you might expect from something that's been programmed before it's gone onto the board. So I suspect maybe this is the JTAG interface they use to program that flash when they're first configuring and sort of testing the board. But none of the other pads appear to have any dimples on it, so it looks like that's the only one that's actually used in production. Let's take a closer look into this front section. Right, so this is the actual imaging sensor on its little PCB. Some test pads on the back there. And the front, the section which I'm guessing has got the calibration shutter in it. It looks like it's this assembly here. Actually, it looks like it's a separate module. This looks like quite a nice, neat little module. It looks like it's built sort of like a camera shutter type thing. There's just a little coil there, so I'd imagine there's some sort of vane that will flip in one of two directions. I'm guessing that's probably the pivot, and it pivots round and pulls a vane up into the field of view. There's no electronics on this, so let's try sticking a few volts up it and see what happens. And actually on this side you can actually see the little lever piece here, which if we move pulls the vane out. I wonder if that might actually just be an electromagnet that's pulling it in one direction rather than a motor. I did notice the power draw went up to, I think it's about 100 milliamps or so additional power draw when it was calibrating, so obviously it doesn't need to do that very often, so the power consumption of this isn't a particularly huge deal. Although one interesting thing is there's no temperature sensor on it. Obviously what it wants from the point of the reference is to know the temperature of that vane, so clearly what they're doing is they're just using the metal housing and making the assumption that this vane is at the same temperature as the rest of the housing. That's probably also why that when you first power it up you get the little tilde sign just saying approximate temperature, so it's allowing some time for the whole thing to stabilise before sort of giving any claim that the readings are particularly accurate. Obviously this sort of sits in here, so the temperature of that vane is pretty much going to be very close to the temperature of the metal frame. But I think, yeah, it probably is quite important that it is in a metal frame to avoid any thermal gradients across it. Yeah, this thing's actually very sensitive. It only takes about 1.5 volts to flip it, and it pulls about 100 milliamps. So it's obviously very, yeah, designed to be very lightweight, low power, to minimise the battery draw. I compare that to the vane in the that firefighter camera that I took apart. I mean, that's got a massive great solenoid and makes a big sort of chunky, clicky sound. So this is obviously a much more refined little solution. And so I'm guessing this circuitry here is probably a little buck regulator to provide that sort of 1.5 volts or whatever to run it, maybe even a constant current circuit, just to maximise the efficiency of that. Right, so this is the actual sensor board, which is where all the magic happens, and this looks like it's just a sort of push fit into this frame here. Oh, now that's interesting. I was really expecting to see a sort of vacuum encapsulated, hermetically sealed thing in here, but because normally they sort of vacuum. You need to have a sensor like this in a vacuum, so otherwise you get, if there's any sort of air or gas in there, then convection currents will cause problems with measuring temperature. But this looks like it's basically a few layers of glass, and maybe the yeah, it looks like it's actually bonded onto this frame. So this obviously is a metal frame, partly to keep the whole thing at the same temperature, and it's actually bonded with bond wires down to the PCB below. Yeah, so I'm actually surprised that obviously this is how they can get the cost down. You know, obviously a metal ceramic package with a sort of window is quite expensive. But interested to know, I presume that must be, yeah, there's actually 2 layers on there. There's a sort of layer on the top and then a second underneath. So in that top layer must be something which is transparent to infrared, so either germanium or zinc, probably not zinc selenide, maybe gallium arsenide or something. But I'm, yeah, quite surprised. I suppose, you know, if it is in a can, then you've got the additional cost of a window on there. So if they can minimise what's in front of the sensor, that's going to have quite a big impact in costs. Right, let's take a really close look at this sensor die. We've got Flir Systems 2009 copyright date on there. So it looks like it's not a brand new sensor for a brand new product. It must be something they've been using in some existing designs. And so this is the edge of the window. If I change the focus, look at the top, you can actually see there is some patterning on it, but this looks like almost like a, you know, please cut along the dotted lines thing. There's just a corner mark and these little dots on the edge. There's no other discernible features on it. Don't know if maybe it's been cut away underneath or something. Now, where these things are generally a micro-machined array, where there's an array of temperature sensors which are partially machined out to thermally isolate them from each other, so each one can sense a different temperature. So I don't know whether this machine part is on you know, the base silicon, and the top is just a cap, or whether it's machined out of the top part. No real way to know without taking it a bit too far apart. So let's have a quick wander around the edge of this die. Just various sort of odd lines and things. You can see the bond wires here. Also what looks like some test pads next to them. You can see there's some gold pads and there's actually some little marks on them, which are probably from the sort of wafer probe test equipment. There's actually some numbers on there, pin numbers. What's on there? Little bits of circuitry there. Interesting looking features there, no idea what those are. And some labelled pads here which aren't bonded. I'm guessing those are going to be used for testing purposes. Here are the pads that are bonded on the other side. Again, there's these gold pads next to them, which I'm sure are for testing. Just a bigger target for the probes to hit than the bond wires. And this edge is very close to the window, so there's nothing there. So it doesn't look like there's a huge amount of circuitry on there. Most of it seems to be sort of wiring, but I don't know enough about silicon to really comment on what this stuff is around here. But it's quite interesting to look at. I'd be very surprised if this wasn't actually a full 320 by 240 sensor. It certainly wouldn't make sense to make sort of quite a lot of, if you look at the 4 models in the E-series, it certainly wouldn't make sense to make 4 different sensors. So I suspect they're probably all the same sensor. Whether there's any sort of selection, they only use the good ones for the high-res cameras or not, I don't know. We can't see enough feature detail on here, I don't think, to be able to actually count anything, because it's all hidden under that that cap, so we need to take that off, which I'm not going to do. Now, looking at this lens mount, this lens does actually screw in, and there's a fairly long thread on it, and I think, just looking at how it all fits together, I think the only thing that's really stopping this being screwed and unscrewed is this rubber surround that just gives it some friction. I think there's actually enough space there that if you have a tool that just engages with these serrated things, it should be possible to actually adjust that from the outside. And of course, for close-up work, what you want to do is actually pull the lens away from the sensor. So I think, given the right sort of shaped tool to actually engage in these little serrations, I think it might be entirely possible to just literally from the front tweak the lens out for close-up work. So once this thing goes back together, I'll give that a try. That could be a very handy feature for doing close-up electronics work. Obviously the visible camera assist wouldn't work, but so this lens, it looks like it's sort of convex on the front, concave on the front and sort of convex on the back. I'm guessing, it's hard to tell, I think it's probably a single element. It's a bit difficult to see. It's so you can't actually see anything through it because it's germanium. It's only passes long wave infrared wavelengths. So this is sort of really the essential core of the whole system. It's just the sensor, it's metal plate, and the shutter, and obviously a lens in front. So there's not actually a huge amount to it in terms of overall shape and size. There's the processing electronics, and the rest is just sort of handle and screen and stuff. It's a very neat little unit, and sort of very nice little bit of engineering on the shutter, and some quite interesting packaging. You don't often see sort of fairly bare silicon with bond wires that's not in a sealed package. And that's still a fairly big die, and that's probably maybe about sort of 9 or 10 mil square, so it's a fairly big lump of silicon. And obviously it's fairly exotic processing as well, so you know this thing still isn't going to be super cheap. But they've obviously done a lot of work in reducing all the packaging costs for these things compared to you know, sort of sealed hermetic can. I would assume that this is probably assembled under vacuum to yeah, the actual lid probably gets bonded on under vacuum conditions to avoid any airflow inside it, to avoid convection currents. But there's obviously not going to be a lot of space inside that. The that top piece is fairly thick. I'd say it's probably about 1 millimetre or so thick, so it may well be actually machined out as into a cavity inside. Right, we've got this thing just running open, just to, I think it's probably time to have a little poke around with the scope to see if we can see anything interesting going on here. Right, the pads on this sensor are actually quite tricky to get at, and there's a few little pads on the top there, but as sort of interesting things quite often get put on sort of more accessible test points, I'll have a little probe around those first before getting into more detail. Now, I was expecting these to be JTAG pads, and maybe some of them are, but found this 74 MHz clock signal on one of them, and right next door what looks like a bunch of data. There's two pins that both seem to have similar data. So if you maybe take a look at the sort of general structure of this data, we seem to have sort of bursts, and let's just see how often those bursts occur. In fact, we've got a sort of multiple levels of burstiness. So if we look at the major one, we have 60 Hertz. That's interesting. And it turns out, if we actually count how many of these bursts, which I've already done, it comes to sort of approximately 240, which is interesting. And if we look a bit deeper at this, we've clearly got some structure here. The content does vary. It's a bit hard to see, but you do see some variation in content. If you wave your hand in front of the sensor, let's try waving a hot soldering iron in front of the sensor to see if we can get some bigger changes. Yeah, and this is clearly sort of arranged in groups of words of some description. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, sorry, 12. Yes, probably either 14 or 16 bits. And it turns out that on each of these sections we've got about 160, and there are two separate lines, and those lines do not appear to be differential, so it looks like we've got two streams of data. We appear to have 320 words of data, which I think that's quite interesting. I've just improved the probe setup a little bit so I can take a look at both those streams. I've got this is a wire with a few amps going through it to produce a nice hot target to look at what's happening on there. Right, so I've just got that whole block. There's 160 words on each line here, and I've just zoomed in so we've got 2 words on each here. If I move the wire through the whole field of view, you can just about see some motion across there. And if I move this wire extremely slowly as it passes through that zoomed area, there we go, move it very slowly through there. Seems like it's appearing on one waveform, then the other, so it's sort of an interleaved data format. Let's draw it again. Very slowly coming in. I'll just put a flat piece of metal straight in front of the sensor so it sees a very uniform flat temperature. You can see there's quite a lot of noise on that, but just so you can maybe have a look at what this data means. I'm just going to hold a soldering iron close to it so it will very slowly start warming up. So I think we can get a fairly good idea of the meaning of that data. We're just getting an increasing temperature, and we're seeing quite an understandable pattern on that data. One thing I haven't noticed on this board is an A to D converter. I mean, that weird data stream we saw implies a sort of data rate somewhere around the sort of 10 megasamples a second at maybe at least 14 bits. And really, I can't really see anything. I mean, that's sort of possibly the only candidate which is vaguely near the sensor, but there doesn't seem to be much. You know, like if that was an A to D converter, I'd probably expect it to have more pins and have some more analog stuff around it. So, and yeah, I've had a quick poke around with the scope. There's no sign of any data anywhere. I just wonder if they've integrated the A to D converter onto the actual die. Yeah, that silicon on the bottom section. Maybe that actually has got the A to D on there, which obviously would be a very nice piece of integration. But integrating a sort of 10 megasample sort of 14 plus bit A to D converter, which obviously needs to be optimized for low noise on a die that's also doing sort of sensing, is a pretty impressive achievement if that's what they've actually managed to do. Alright, just a few thoughts about these unpopulated connectors. So there's this one here that looks like sort of probably a board stack type connector, and there's an unused flat flex connector here and an unpopulated FFC connector there. Both of those have cavities in here to go up. Interesting that production test connector. Peel this off, there's a bit of rubber in the way, but sort of accessible through there. You'd need a special jig or something to get the cable in, but I wonder if maybe when they manufacture them they stick a bit of flex in there, assemble it leaving the flex hanging out, do the test and then just pull the flex out and put the label over. Now if you look through the upper range, the higher ones in this range have Wi-Fi, so clearly one of those is going to be for a Wi-Fi module. I'm guessing possibly that one. There's maybe a board that plugs in there. There's also Bluetooth. Whether it would be a combined Bluetooth and Wi-Fi module, whether there's a separate connector to Bluetooth, I'm not really sure. This temperature sensor just got this sat wheel. I'll just put a cover over the lens so it sees a fairly flat background, and this is showing a temperature range between 25 and 34. If I just warm this sensor up by sort of sticking my finger on it, what we should see is next time it does a calibration, those figures going down. Yeah, see, that's just suddenly dropped to 24 to 18 because it's now the reference temperature is actually higher, so it's thinking what it's seeing through the sensor is lower. And just a more extreme example, if I just give it a little squirt of freezer. You can wait for a calibration. I think it took a bit longer doing that calibration. It was maybe thinking, so now it's thinking sort of 235 because this sensor's now so cold. It's saying minus 40, so it's. I think that maybe it was so cold that actually something overflowed and it's just gone completely crazy now. So we just give it a little chance to settle down a bit. I think it's just got itself very confused now. It's not expecting to see that temperature sensor down at sort of minus 40 or 50 or whatever that freezer takes it to. Oh, here we go, it's slowly starting to come out of weird. There we go, so it's now recovering. Now, as I mentioned before, the pin out of this little chap here absolutely screams I2C E2 prom. You can't actually see it here, but that pin's grounded. We've got pins 5 and 6 connected to pull-up resistors and power up here, so that's just the classic pin out for an I2C E2 prom. I've also just done a continuity check and that actually does match up to the I2C pins on the real-time clock chip on the other side of the board. Yeah, this little button here, I couldn't seem to get it to do much. If it's pressed while the thing's powering up, it does seem to stop and stall the power up process, but other than that I couldn't get any obvious visible effect from it. Let's take a quick look at what's happening on I2C. Fortunately this connector has actually got the I2C bus available, so I've just plugged a little bit of flex cable in it to a connector so I can just hook up to it easily. This Agilent scope's actually got some really nice features for decoding I2C. it's got I2C analysis, so it will decode packets. Say here it said that, you know, write to address AA with an acknowledge, data A to acknowledge, restart, address AB, read acknowledge, and that's the read data, so that's a single byte E2 prom read. But it's actually got quite a lot of higher level stuff. For example, it's got trigger, I2C trigger, so you can actually trigger it on various conditions, including an E2 data read. So you can make it just trigger when it reads. But the other nice thing is segmented memory. So instead of triggering once, because quite often what happens is you get like odd reads dotted around and a huge amount of space between them, so that would sort of typically fill up the acquisition memory. But with segmented memory, it will just trigger on each trigger event, in this case an E2 read, so you can capture quite a large number of reads. So this is in segmented memory at the moment, so as I'm changing the time, it's stepping from, you know, one event to the next, so it's got a few bursts there. But it means you can capture data that's happening over quite a long time. It's also got this nice lister mode where it actually will give you a sort of listing of it, including timestamps. And what it can then do is you can actually export all this data in CSV format, so you can actually take all that data, which obviously, you know, in some cases could be quite a lot to search through, and just dump it to the computer to actually sort of look at what's doing. So for example, you could look at what the contents of the E2 prom were just by its response. Obviously you can just read an E2 prom out of a device, but what that doesn't tell you is which locations that device is actually looking at. So, you know, if you've got a huge E2 prom full of all sorts of data, at least as useful is knowing what data that device accesses when, to just get some insight into the actual meaning of that data. Right, so you can see we've got various bits of data from the E2 prom reads. Looking at the values, a lot of this is clearly ASCII. So for example, here we've got FLIR E4, so that's the make and model number, and then we've got things like the serial number. One thing that's quite interesting is over here we've got 2013-10-02, which is the day before the day on the calibration certificate. So this is clearly data that's written at sort of the time of manufacture. And poking around on that same connector during power up, I found what looks like a serial port. And this is what it says when it starts up. There's a few interesting things. This is obviously the Windows CE boot up screen. A few interesting things you can see in here. So for example, here it's got the screen configuration 320 by 240. Battery fuel gauge firmware. I wonder if there's actually a fuel gauge device in the battery, or whether that's one of the devices on the main board. And looks like this is configuration kit E4, so that's probably the device features that are enabled. Various mainboard serial numbers, that sort of stuff that's in the E2, I think. It's interesting, it's got a serial number for the camera core. I wonder if that's in the E2 data or if it's reading it from the camera. 6804. Yeah, that's in the E2 as well, so that's one of the other bits of manufacturing data that's probably stored. And a few things, so no WLAN capability, so say there are versions of this with Wi-Fi, so it's obviously not detecting the hardware, so it's not trying to start up the wireless LAN stuff there. Again, saying here platform does not support Bluetooth, so it's probably not detected any Bluetooth hardware. And some interesting stuff here, not adding menu item due to cap, so presumably these are some of the features in the higher end models So voice, toolbar zoom, picture in picture. So this is all the stuff that's not supported in this model. And something here right at the beginning is this sort of loading FPGA.bin. So this is going to be the FPGA configuration file, which it's loading, you know, very early on in the process. So as we saw, when you turn the thing on, you get the image very quickly while Windows CE is still booting. So it's obviously pretty much the first thing it does is configure up the FPGA. And there's probably some other bits here that are just getting enough software initialized just to display the image on the screen while the rest of it's booting up. Again, I don't have time to play at the moment, but I suspect I might take a look at this at some point in the future. This is the battery. It actually snaps into the bottom of this piece, but there's actually quite enough space in there to have put a tripod mount, so I don't quite understand why they wouldn't do that. Okay, you probably wouldn't use this very often on a tripod, but obviously the fact you can tether it to a PC and do video through it seems a little bit of an odd omission, but I think there would actually probably be enough space to, if you could find a sort of just a sleeve type mount, you might actually be able to drill that out and get it in there. And so this is actually sort of fairly tricky to get out, so I'm sure that, you know, if you buy a replacement battery, you almost, I'd imagine you probably get this whole thing rather than just that part. Slightly wasted opportunity, but it looks like it might be moddable, so not a huge deal.